Hi, I'm Cass. This is going to be a short lecture series, kind of covering the interesting parts that mechanics has to offer. So you're kind of going to go through this over your first year or two if you're in TP. If you're going into physics, a lot of the first parts will be covered, but some of the second half of the more interesting stuff we won't cover in class. So although it's not covered in class, it's still really cool. And if you have any interest in more math side of physics, it's definitely worth going over. So first of all, kind of some prerequisites that you need. This is like the math type of stuff, is really just kind of like vectors and trig. If you've seen, or if you've done leaving cert applied maths, that type of thing, you'll be pretty handy with vectors. There's some notation types of things that we'll go over, but nothing too new. We'll have a look at like matrices and that type of stuff. So again, nothing too out there, but worth understanding. And your basic trig that you would have done at junior cert and leaving cert, that's all that's kind of required. The other kind of mathematical prerequisite we'll have is calculus. A lot of the kind of basic stuff we'll already have done in leaving cert. So like basic limits, differentiation, integration. The only kind of new thing we'll be looking at, other than just techniques and practicing those, is partial differentiation. But that's nothing to worry about. We'll cover it when we get to it, but it's really pretty much the same thing that normal differentiation is. Moving on to the second part of the course is motion dynamics. So this we'll cover your really basic mechanics that we would have done in the old applied maths course. I'm not sure about the new one now. But say motion of just like motion of particles, projectile motion, that type of stuff, how a particle will move. Normal kind of dynamics. But again, these two are kind of very basic, just getting your brain back into the idea of thinking about classical mechanics. The last thing that we'll do in this section is systems of multiple particles. This we wouldn't have done in leaving cert, but it's nothing too big to worry about. And that first half should be done within, I say half, it's not really going to be a half of it. But now the second section really is really where we get into the most interesting stuff. So the first thing we'll do in the energy and action section is just going back over energy, right? What we mean by energy in physics, different types, how we're going to be using them mathematically, the ideas of like conservation of energy, that type of stuff. Nothing too big. We'll then go into something called the principle of least action. This is really when we start getting to the cool side of mechanics, right? Now the word action should not mean anything to you in a physical or physics-based context. You would never have come across it by doing anything in leaving cert, really. But it's going to be something that's incredibly important from your time studying classical mechanics all the way up through quantum mechanics. Everywhere in the universe is defined using some form of action and the principle of least action, or stationary action, as it might be called. And to really take these physical principles and then use them, we need math to back it up. And a lot of this maths, from a classical mechanics point of view, is defined in the order Lagrange equations. That these are like insanely central to our work in classical mechanics. I think you'll go on to it in second year of TP if you do it in advanced classical mechanics. You'll cover these. Now they're so central, and in the notes they're written so much, and anything I write up here, I will most likely just refer to them as ELE, because they're just written that much. The shorthand notation is quite useful. The last part we're going to cover is on symmetries. So this isn't symmetry in the geometric idea that you might have had already. These are mathematical symmetries We'll cover them when we get to them, but up until then, we don't have to worry about the kind of math side of it too much. The first thing we'll go in there is the connection between symmetries and conservation. So you might have heard of laws like the principle of conservation of momentum or conservation of energy. All of these things that really are the kind of the backbone of our understanding of physics can be mathematically derived from different symmetries. So we'll kind of see how that goes. And using this information of symmetries and conservation laws, we can build off another formulation of mechanics. Now, what I mean by formulation is kind of a mathematical framework of how to attack or how to model systems in the real world. So you would have been, and what we'll cover in the motion and dynamics section, and what you would be more acclimatized to as of now is Newtonian formulation of mechanics. So your F equals ma, all of that stuff that you would have covered beforehand, and we'll cover in motion and dynamics as a refresher. That's called the Newtonian formulation of mechanics. The next one we'll do is the Lagrangian formulation of mechanics. This is like using the action, and we'll see what all that, how all that kind of fits together. And lastly is the Hamiltonian formulation of mechanics. And this is, again, very useful, not only from a classical mechanics point of view, but even throughout quantum, and even in your first quantum class, you'll see that a Hamiltonian will pop up somewhere. And as you go on through your career, you'll see it again and again and again. Hamiltonian, coming from William Rowan Hamilton, which, if you're studying at Trinity here, was an alumnus in, I think, the late 19th century. So kind of nice to have some Trinity somewhere in mechanics. The penultimate topic that we'll be covering is the phase space fluid. Now, this shouldn't really mean anything to you now. It will by the time you get to it. But yeah, it's not really something you have to worry about too much now. And the very final thing we'll cover is Poisson brackets, named after the French mathematician, not the French word for fish. Yeah, and that's kind of a good outline of the kind of topics we'll cover. The bulk of it is towards the end, the energy at action and the symmetries, but having a good understanding of your math behind it and the Newtonian physics is going to be key to going through it. So yeah, that's the introduction done.